Hello everybody, this is Dr. Christopher White, and in this video we're going to be looking at exercise 15 from Interpreting Earth History by Ritter and Peterson. Okay, so you're going to want to turn to page 224, and on page 224 you'll find out that we are dealing with Paleozoic Orogenies of Ancestral North America. So we're going to be focused on the eastern coast of North America. So obviously, just like previous exercises, there's the purple box listing the objectives, and there is a bit of text here essentially introducing you to what was going on. Now it's actually quite a short piece of text, there's not too much information in it, so we're going to come to this diagram in just 1 second, and then we are straight in to part A. So in terms of this diagram here, this diagram is an absolutely beautiful diagram. And what it's showing you is it's showing you the foreland basin of the Taconic, Akkadian and Alleghenian Orogenies. So you're thinking, what is the foreland basin? Well, the foreland basin is a depressed piece of crust that develops during mountain building orogenies. So this depression obviously fills with water and it becomes a basin. Okay, so essentially a small body of water. And this body of water will obviously fill with sediment being eroded from the mountains that form. So if we look at this particular diagram here, you will see that it's split into tectonic cycle 1, tectonic cycle 2, and tectonic cycle 3. Tectonic cycle 1 essentially is the Taconic orogeny, tectonic cycle 2 is the Akkadian orogeny, and tectonic cycle 3 is the Alleghenian orogeny. So what we can see is all three of these mountain building events have ended up depositing sediment into this basin. So initially we have the basin itself, the depressed area of crust, okay, forming due to the Taconic orogeny, and then we have sediment being deposited essentially over the basin during the latter stages of the Taconic orogeny. So during the Taconic orogeny, the basin was actually filled up with sediment. Then have sediment coming over the top of it. Now, during the Akkadian orogeny, we can see we begin to actually build a pile of sediment on top of the fallen basin. And then during the Alleghenian orogeny, you can see we have even more material being deposited over the top. So this fallen basin that developed during the Taconic orogeny filled up with sediment, and then additional sediment was piled up on top of it. But what you're seeing is the results of mountain building, and this is very, very important to remember. Mountain building events produce huge quantities of sediment, and that sediment has to be deposited somewhere. Alright, so what are we doing now? Well, we're going to go on to part A. So part A, what are we doing? Well, question 1. What are the 4 principal kinds of rocks exposed in the map area, of the map area being figure 15.2, and what are the ages of the exposed rocks? Well, here we go. So here's our map. Very, very simple map. And you can see in the top right we have ourselves a key. Obviously we have the ages of the rock here. We have the rock colours and rock codes here, and we have the descriptions of the rocks here. So I think part 1 pretty much answers itself with very little effort. So what about part 2? So using the figure below, draw a graphic cross section, I'm sure your heart just sank, along the diagonal line labelled A to A prime on figure 15.2. Assume that the fault plane between the Rye and Kitty formations dips 80 degrees to the southeast. Okay, so where's the Rye and Kitty formations? Okay, well, let's find what the Kitty formation is. The Kitty formation is SK, and we can see here's SK down in the lower portion of our diagram. Okay, and the other unit is the Rye formation The rise formation is here. It's this kind of grey-purple unit, and we can see that, there we go, it comes in like so. So the contact here between the two of them is marked out by this big, thick, dark line. That's obviously a fault plane, and that fault plane is going to dip at 80 degrees to the southeast, so essentially 80 degrees towards A prime. So when you draw that on your cross section, you're going to be drawing it dipping 80 degrees towards A prime. Okay, in terms of the dip information that you have, this is a extremely straightforward cross section. So up towards A here, we start off with a little bit of granite, and then we come into a layer of rock that's dipping 70 degrees towards A. We continue into the next unit that's also dipping 70 degrees towards A. We then hit another granite. We then have a unit that's dipping 72 degrees essentially towards A prime, so it's dipping the other way. So as you can quite clearly see, we obviously have ourselves an arch right here, don't we? Okay. Then we have another unit which is still dipping 70, I can't quite work it out, actually 70 degrees, sorry. Then right here we have a unit which is dipping 58 degrees towards A, so we now have a trough. Then as we come out of that, 60, 59, so essentially we have ourselves an anticline, syncline pair, which is a classic sign. And then when we come over here to ORV and ORM, what do we see? Well, we see that first of all they're off the shot there. There we go. Well, we see that this side of ORV and the northwestern side of ORM are dipping towards A, but then we see that the eastern side of ORM is dipping away from A. It's dipping towards A prime. So this on the whole is quite an easy cross section. So how are we going to be drawing this? Well, the fault, as we know, is dipping 80 degrees towards A prime. So now we have to think about what we're going to do about the granites. So when it comes to the granite, what we're going to do is we're just going to try and keep things simple. Now obviously, as we've dealt with in the past, we don't actually know exactly what the granite's going to do, but you know, you can honestly say that the granite is going to be near vertical, so I would just draw it as a, you know, a line coming down like so. And then when it comes to this granite, essentially, when it comes to this granite here in the middle of the map, well, I would just do something similar. I would draw it, you know, as a granite coming down like that, and a granite coming down like that. Okay, so you have a granite like so. All right. Now then, obviously, as we know, we have rocks on this side of the granite, which are dipping at 70 degrees or so. So these units are obviously dipping down in that kind of situation, aren't they? Okay. Now a little bit of artistic license. I'm just going to put a bottom to this unit here. Okay. And then we know when we come on the other side of the granite here, we know that all of a sudden the dip is now towards A prime, and that continues on the other side. So we know that the layers of rock that we have here, well, they're starting to dip towards A prime on this side, so they're going to be coming down like so. And then we have ourselves quite a broad syncline, which essentially the middle of it is going to be approximately here. Okay, so I'm actually just going to drop my fault in, just to, so there's my fault, is going to come down like so. Very, very steeply, remember, 80 degrees towards A prime. So I'm then going to end up with a very, very broad syncline coming round like so. Then another layer of rock underneath it coming round also kind of like that. And then on this side, what I'm going to end up with is I'm going to end up with a layer which is coming down like, well, it's going to be coming down like this, essentially. Okay, and then we know that it's the anticline is coming around like here, but we can't really draw that. And so this is essentially going to be the cross section. Okay, relatively straightforward, nothing too complicated. Obviously, you know, you're going to have to draw it. So just like we've done on the previous ones, you know how to do this by now. Get the image, dump it into something like PowerPoint, draw yourself a rectangle here, okay, mark the transitions. They're quite big chunky beds of rock, so you know I think you should be able to pull this off pretty quickly and pretty easily. Okay, obviously please remember, when you take your screen grab of this and you take your screen grab of this, your magnification on your page must be the same, otherwise they will not be equal in size. So just please bear that in mind. Okay, so I'm now going to erase this. So just please bear with me for a second, so that you guys can't see my wonderful handiwork. But let's face it, you could just pause the video, so you know I'm not that smart. Okay, so on to question 3. Well, question 3 asks, what type of fault separates the Rye and Kitty formations? Okay, well, this is an interesting question. So, okay, here we go. We're coming over to the Rye and Kitty formations. Well, what do we have? We have SK, that's Silurian, in contact with ORV, which is Ordovician. So, that's a bit of a tricky one to work out. If I had to guess, I would say it was a reverse fault, because if you remember, thrust and reverse faults tend to push older rocks over younger rocks. So, you know, if I had to take a swing at it, I would probably go with thrust. However, you know, maybe you could argue something else. There is also the possibility that, you know, it's actually quite difficult to work out exactly what the difference is, because if you look, these two are exactly next to each other in the key. So definitively proving what kind of fault it is, well, that one's actually, you know, a little tricky. So, you know, I would probably take a swing at a reverse fault, but at the same time, if you were to write, I'm not really sure, that would also be a pretty valid answer. Because, you know, there's a lot of openness, essentially, a lot of confusion in exactly how that fault is working. So, when we come on to question 4, question 4 has lots of text, okay. What episode of orogenic activity in the history of the Appalachian Mobile Belt is responsible for the rock types and structures present in the portion found in New Hampshire? Cripes, that's a lot of information. You may wish to refer to figure 17.1. I don't need to refer to figure 17.1. I have something even better. And here it is. If I just come over here to my lecture, then what I'm going to do is I'm going to expand this, and you can see we now have a nice big map of North America with the Orogenies marked on it. So if we look over here, you can see we have the 3 Orogenies that make up the Appalachians. So we have the Taconic in red, the Acadian in green, and the Alleghenian in pink. I should have moved these text boxes a little bit closer, but alas I didn't. Silly me. So what we can see here is we can see that we have, essentially in terms of the order, the Taconic orogeny came first in the Ordovician. The Acadian orogeny came second, with most of it occurring in the Devonian. And the Alleghenian occurred last, essentially between the late Carboniferous and all the way into the late Permian. Okay, so what we need to do is we need to work out which one of these 3 orogenies will explain what we can see on our map. Alright, so let's just jump back to our map. Here we go. Okay, well, what can we see right now? Well, we can see a few things. So number one, we can see we have our granites, can't we? We've got there and there. Now, granites are often associated with volcanism. Okay, so volcanism is, you know, very commonly associated with some kind of tectonic activity. So there is the possibility that these granites represent, the feeder material for volcanoes erupting at the surface. We can also see that the Silurian and the Ordovician rocks have been deformed. So this means obviously whatever deformation is taking place, it must be post-Ordovician and post-Silurian, because these rocks have been deformed by that orogeny. So what can we say? Well, the orogeny is obviously post-Ordovician, so we can see the Silurian rocks have been deformed. So that means we can obviously go and say, well, right, it can't be the Taconic orogeny, because the Taconic orogeny was early Ordovician to late Ordovician. Now that would mean the Silurian rocks wouldn't be deformed. So okay, we can forget that, can't we? Okay, so what's the next orogeny? Well, that would be the Akkadian orogeny. Now that would be early Devonian to late Devonian. Now I think we can agree that would be pretty perfect, wouldn't it? So being Devonian, it would allow us to deform the Silurian and Ordovician age rocks, and it would also explain the Devonian intrusives, because that would explain, then you could say, right, these represent magma chambers feeding volcanoes at the surface. So, I would say that represents a pretty reasonable explanation of what the likely orogeny was. On the other hand, you may disagree with me, and you may think it was another one of the three orogenies, in which case, okay, try and make your point. Alright, then there's question 5. Are the rocks and structures in this area the products of convergent, divergent, or transform margins? Okay, well, once again, we've discussed this in the past, so we're not really going to worry about it too much. So in order to deal with this problem, I am going to grab myself a post-it. Here we go. So we have ourselves a post-it note. Obviously, we know when forming things like folds, and so if we are divergent, so we're actually opening the crust up, we are pulling. Does that end up forming any kind of fold? Let's see. As we stretch our piece of paper, no. Okay, what about transform? Well, in transform, obviously, we're trying to pull one piece of rock past the other. So away we go. Not exactly forming any folds. The crust buckles a bit, but it doesn't exactly form folds. So, all right, forget transform. On the other hand, if I start pushing my post-it note from either side, aha. Okay, so I think you can probably work out the rest from there, can't you? Alright, so that's part A. So part A, although it does involve a cross-section, I would say is nowhere near as horrible as, the previous cross-section. Okay, so what are we doing next? Well, we're not doing part B. We are instead going straight to part C. And part C deals with, if we skip the key for a second, this map right here. Now, I think there's a very good chance some of you have gone, oh, what is he giving us? And it's not as bad as it looks, though. Okay? Now, by now, I'm sure you guys are spotting that what we clearly have here is some folding. And you can see there's folding because we have repeating layers of rock either side of the hinge of the fold. Okay? You can also see we have that classic, pinch off as the fold gets thinner and ends. We can see it here and we can see it here. So, okay. So, you've already worked out we clearly have a very strongly folded terrain. Now there are a lot of rocks on this map, so we have 2 full pages for the key. Okay, so let's start. Question 1. What is the likely source area for the Ordovician Martinsberg Formation and the Devonian Catskill Formation in figure 15.1? Okay, what mountain building events are associated with these formations? Cite your evidence. Alright, so one of them is Ordovician and one of them is Devonian. So we were just talking a second ago about which orogenies would be associated with those time frames. Well, we were discussing how the Taconic orogeny was early to late Ordovician, and the Akkadian orogeny was early to late Devonian. So that would tie in reasonably with these two formations, wouldn't it? So, citing my evidence, well, my evidence is literally that that's when the mountain building events happened, and of course, the deposition of such quantities of sediment would be consistent with a mountain building event, and that mountain building event being eroded away, producing quite large quantities of sediment. Okay, question 2. So using the geologic map found on page 234, which we just saw a second ago, account for the differences in the structural patterns north and south of the Pennsylvania Turnpike, which extends east-west through Carlisle, Pennsylvania. Okay, so if we look for the Turnpike, I actually spent a minute finding it earlier. It actually runs, lost it now, there you go, it runs through here. Okay, so we need to try and explain what's going on between these two different terrains. Well, what can we see? Well, we can see that this southern terrain, okay, contains several large, thick black lines. We know by now that says faults. In contrast, this northern portion, well, it's pretty fault-free, isn't it? Not much going on there. So, how do we explain what's going on? Well, clearly it's got to be tectonic, hasn't it? We can see that this sequence here is essentially a mixture of Cambrian and Ordovician material, which has been quite badly faulted. Well, we can also see, by the way, that these faults actually follow the folds. So how can we explain what's happening? Well, imagine this situation. Imagine we have a situation where this area of rock is being deformed by the tectonic orogeny. And tectonic orogeny is stressing this area so much that it starts to fault. Okay? Now, then later on we have the Akkadian orogeny come in. Okay? So the Akkadian orogeny then dumps a whole pile of sediment over the top. Alright? And then what it does is it then ends up folding the entire area. Now I'm just going to go back just for 1 second to the key for just a moment. So in terms of what's happening, please give me just 1 moment. Okay, so possibly, I stress possibly, this folding that we see here could be due to the Akkadian orogeny, or it could be due to the later Alleghenian orogeny. We can't really be sure at the moment. But what we can see is we can see that these fault planes are associated with these folds. So what we have here is we have a whole sequence of sediments which are deposited north of the turnpike, and in this area we can see that the sediments, if they were present, have been eroded away. Now that might be due to the faults pushing up the sequence and the sediments being removed. What we can see is that whichever event has ended up folding this sediment here has also ended up folding this sediment here. So we can tell that because if we look at the alignment of the folds, so they're aligned this way, and these folds are also aligned in the same orientation. So they're part of the same event. And we can tell that the event has also gone and folded the faults here because we can see how this fault bends with the fold. Okay, so we know the fault must be older. So what we're seeing here is we're seeing that yes, these two areas are tied together because they do share some structural similarities. So in this case we can see they've both been folded at the same time. However, this area represents an area which is heavily faulted and it doesn't have the same cover. Now this could be because, as we discussed, the faulting pushed that cover when it was deposited on top of it upwards, so it was eroded away, or the cover was never deposited. I'm sorry that this is a bit of a rambling analysis, but this is kind of how it works. So that's a kind of general description of the kind of thing we can see here. I would advise you to listen to what I'm saying and try and make some notes and try and work it out from the from what I've just said. Okay. Question 3. So, date the Appalachian folding in this area. Surmise the evidence. Okay. So, I should say summarize the evidence. What am I saying? Surmise. Okay. Well, let's try and date when the folding occurs. So, obviously, in order to date the folding, we need to find the youngest rock that's been folded. So, okay, here we go. So, this rock here is right in the core of this fold. Possibly this rock over here, which you can't see because that rock may be as well. I'm going to try and find what this one is. Okay, well, these rocks over here, they are Silurian, so they're probably not going to do it for us. So let's move over here. We got Devonian, Mississippian. Okay, this could be our youngest rock here. So this is MMC. If we come over here, MMC, and above that, okay, good. PP is a blue-green, so this is going to be Pennsylvanian. So this is our youngest rock. So we can see that deformation in this area is essentially late Pennsylvanian or Permian. All right, so that only really, that's only really associated with one of the orogenies. It's the Alleghenian orogeny, because remember the Taconic orogeny is Ordovician, the Acadian orogeny is Devonian, so that only really leaves us with one option, doesn't it? We can't really be anything else. So we've managed to answer that one. So in terms of when it started, it's definitely got to be post-Pennsylvanian, hasn't it? Or at least late Pennsylvanian to have folded this. In terms of when the deformation started, well, that's a little bit more difficult to work out, purely because this area will have already been deformed. It will have been affected by the Taconic and Acadian orogenies. So trying to work out exactly when things started, when things ended would be a bit difficult. So, do you know what? Actually, no, I'm making absolutely no sense. Let's start that all over again. I'm sorry, guys. I'm spouting complete rubbish. Okay. So we know that things must have started essentially in the late Pennsylvanian. Okay, so late Pennsylvanian to very early Permian. That explains how this Pennsylvanian rock can be folded here. In terms of when the process finished, well, if we look down here, we can see we have a pile of Triassic rocks. Now, these Triassic rocks have not been folded. Okay, they're a bit messy, but they haven't been folded. So this obviously tells us that these Triassic rocks represent rocks that were not essentially affected by the orogeny. So that would mean that the orogeny therefore must be dated between the late Carboniferous and the late Permian. Because remember, by the time we're in the Triassic, the orogeny stopped. So okay, so that's far more logical, isn't it? Orogeny starts late Permian, orogeny starts late Pennsylvanian and has to have finished by the late Permian because the Triassic rocks aren't affected. Okay, now that's the kind of logic there. There we go. That makes a bit more sense. Okay, so explain the origin and distribution of the igneous rocks in the area. With what episode of mountain building are they associated? Okay, let's try and work that out. Well, what age are the igneous rocks? Well, let's have a look. Okay, well, let's see. Well, no, that's not it. So we need to find ourselves some igneous rocks in our sequence. Well, there's a whole lot of limestone. Can we find ourselves something igneous? Can we find the igneous rocks? Okay, here we go. So we've got some Triassic rocks here. And I think that's pretty much it. See, the problem is these igneous rocks right at the start, they're undated, so they can't really do us much good. So all the igneous action is happening down here. Now we can see some of these igneous rocks have been folded. Okay, so that would suggest they were at least present during the Alleghenian orogeny when the folding here happened. Once again, we can see the folding is parallel with everything else. Okay, so I'm just going to pause here for just a second because I just need to check something. Good. So yes, so these layers here represent metabasalt. So these are essentially metamorphosed igneous rocks. So these are, as you can see, consistent with the Cambrian rocks here, which have been folded. So these metamorphosed igneous rocks are consistent with everything else we can see. So in terms of the rocks that haven't been folded of igneous origin, we can see it's these dikes right here. Now they are Triassic in age. So we know that by the time that this was happening, well, all of the orogenies, they had stopped, hadn't they? Because by the Triassic, essentially Laurasia should I say, and Gondwana, well, they've crashed into each other. So we have to think to ourselves, well, what could these igneous bodies represent? Well, the thing is by the Triassic, we have the first early stages of Laurasia and Gondwana starting to pull themselves back apart. So there is a very realistic possibility that these dikes here represent extensional features. Okay. Now, unfortunately, they don't say what the dikes are made from, but they do say dark grey igneous sills and dikes, which would probably, suggest something like maybe a basalt. So maybe something mafic, and obviously that would be consistent with their divergent plate boundaries, wouldn't it? So yes, these dikes here are probably extensional features, and they're probably the result of the crust beginning to stress itself, and as the early stages of the separation of Laurasia and Gondwana got underway. So then we have question 5. Question 5 is, what is the reason for the present course of the, not even going to try and pronounce it, river? So one of the things we know is that rivers do have a habit of following rocks and faults. Well, what we can quite clearly see is this river is not paying any attention to geology whatsoever, which is a bit weird. Now, what we do know about the Appalachian region, of course, is that it's quite hilly. There are quite a few hills and valleys in the area, and these hills and valleys are the result of folding, the folding of the basement rock. So logically, you would expect the rivers to follow the geology and orientate themselves like so. However, this river does not. This river just smashes on through. Now, okay, you could say, well, maybe it was human. Maybe it's human damage that did this. Maybe we did it. Well, the thing is, as you can see, this river's taking quite a meandering course. If it was humans doing this, obviously we would cut a straight channel. So it's probably not us. So the thing is that what you don't know is that this area, the area of the Appalachians, was actually eroded completely flat by the Cretaceous. I mean, completely flat. It was Houston kind of flat. And so this means there was absolutely nothing stopping the rivers going wherever they wanted. So then later on, when the area started to rise again, producing the hilly terrain that we see now, well, the rivers, they were already exactly where they were, and so they just cut down through the hills and valleys that started forming. So what we're seeing here is we're seeing the result of the area being planed completely flat by the Cretaceous. And then finally, question 6. In terms of plate tectonics, what type of plate interaction essentially produced what we see? Strike slip, compression. So, well, I think we can probably work out what it is. In terms of citing evidence, well, we know that folding and faulting, we know that folding is very commonly associated with compressional tectonics. Now, but also at the same time, we do have some late stage extensional tectonics creeping in, don't we? Okay, everybody, that's it for exercise 15. I do apologise for getting a bit lost in the middle of part C, but hopefully I ended up making sense in the end. Alright, so take care everyone, see you soon.